So I'd like to thank Una for organizing this wonderful summer school. As she mentioned, I intend to be here for the whole time. But trust me, I would have preferred to be here rather than being in a boring meeting like that. But I think I didn't really have a choice. So I was looking at the lecture program, and I realized that there are a lot of interesting, mostly actually theory lectures. And I also noticed from the posters that you guys already know a lot about theory. So I thought, my job here is to make some kind of contact with a real experiment. And the question is whether we can actually interpret any of the experiment using these novel ideas that you guys heard about and you guys actually working on right now. So I'll try to see whether I can convince you that all the exotic phases of matter is not just a theoretical fantasy. Maybe somewhere in the material we may actually see some evidence for that. So here is the outline. So I'm going to give you a quick reminder about what kind of topological phases we'll be talking about. So you already heard a lot about it. So I don't think that it requires a lot of introduction, but I'd like to give you some quick reminder. Then I'm going to switch the gear, and I'd like to talk about it's real materials with a strong spin-orbit coupling. We think that many of these topological phases may be realized in this kind of system. And then I'm going to mention two specific systems. So there are some class of material that we call Ttire material, in quotation. And we think that quantum spin liquid phases may be present there. And then I will talk about some physics of particle iridate. If I have time, then I may go into superconductivity in this kind of system. OK, so I'm going to tell you how to interpret the experiment. But in physics, we need creativity, of course. But we have to be also reliable, right? So there's this scale that we talk about a lot. So you take a creativity and reliability. You take the ratio. You take the logarithm. Then you decide whether you're in the positive side or negative side. This is a friendly scale because you can be infinitely creative and infinitely reliable. You can have 0. So so we usually normalize this scale by putting Philip Anderson at +10. Then you can decide where you are. So I think once Steve said that it's so much fun to be up there in the positive side. So I think maybe I will take a similar approach here. Okay. So quick reminder about topological phase of matter. So nowadays there are many classifications of topological phases, but largely in a bigger scale, I would say there are two classes of topological phases. So the first one is so-called intrinsic topological phases, and I think this is a new point I'm not familiar with. So so the way to think about topological phases, there are many ways to do this, but this is one way. So think about some arbitrary topological phase and try to see whether I can connect this phase to simple phases of matter, like simple band insulators or metals. So if there is no sort of the path that connects these two phases, meaning more precisely, if there's no local unitary transformation, well, there's no way to close the gap when we do this, when I go from here to the other phase, then basically if this phase is not connected to simple phases, we can say this is intrinsic topological phase of matter. So examples are like a quantum Hall state and the quantum spin liquid. And spin liquid is essentially correlated quantum paramagnetic state. I think I'm going to use this one. So I think a lot of you already know a lot about quantum Hall state. So I'd like to talk about a spin liquid. So this is one way to think about quantum spin liquid. So this is essentially a quantum paramagnet, meaning that Okay, sorry, actually, this is a new pointer I'm using, and I think I'm basically screwing up. Okay, so this is a new kinds of, sorry. Okay. So this is a quantum paramagnet in the sense that there is no magnetization in your system. And this is a correlated insulator with no broken translation symmetry. So one way to think about this is to you basically start from a singlet valence bond. So imagine that I start with a spin singlet. So for nearest neighbor site, I make a spin singlet like that. And imagine that I put this spin singlet on a lattice like this. Then, of course, by doing this, I immediately achieve the fact that the expectation value of spin operator is 0, because my fundamental unit is essentially a spin singlet. So by construction, I have no magnetization. But if I do so, then I'm breaking translation symmetry. So I'm violating this principle that I like to have a correlated insulator with no broken translation symmetry. So one way to fix that is to think about all other possible configurations of a diamond covering or the valence bond covering. Then you just take the linear superposition of this. Then notice that by construction, it's a quantum paramagnet. But since I'm superposing all possible diamond valence bond configurations, basically I'm restoring translation symmetry. So this is one way to think about quantum Spinnaker. This is called resonating valence bond state. And this was originally proposed by Phil Anderson and elaborated by Loxar Kiberson. So you can think about this resonating valence bond state as a linear superposition of this valence bond covering. Okay. So to describe this, it turns out it's useful to start from a PCA superconductor. So you may wonder why I want to talk about superconductor when I'm talking about quantum Spinnaker, and you will find that out pretty soon. So this is the usual PCA superconductor Hamiltonian. So I have a hopping term and the pairing term. We know how to solve this problem. Basically, but imagine that I can also go to a momentum space like that. So I'm talking about here some kind of spin singlet superconductor. So this is the PCA wave function with the usual UK and VK vectors. And this is the quasi-particle spectrum. This is what you are familiar with. So now let's look at this wave function. And there are different ways to rewrite this. So for example, up to a normalization, I can rewrite wave function like that. So that's pretty simple. Then you can also see that I can exponentiate this guy and rewrite this part of the wave function like this. And the reason is very simple, because if I have, say, ck up dagger square, then it will be 0, right? So if I expand this exponential, all higher order term will be basically 0. So this is sort of empty statement, but you can rewrite it as a product of exponential factors like that. So then you also realize that you can rewrite this as an exponentiated sum over k of this vector. And that happens because Fermi operators at different momentum, they commute, right? So I can definitely do that. So then notice that this is a nice form in the sense that essentially I'm talking about a Cooper pair wave function in momentum space. And this is the amplitude. This is essentially a pairing wave function in momentum space that's given by the ratio between UK and VK. So now if you do the Fourier transform, then I can do the Fourier transform here. Then I end up with this real space wave function form. And notice that G r minus r prime is really a pair wave function for this pair at the position r and r prime. And this real space pairing wave function is essentially the Fourier transform of this vector. So this is the famous real space form of the PCS wave function. I couldn't find this in any textbook, but I think people know about this somehow.
There is one textbook.
Huh?
There is one textbook.
One textbook?
Anthony Leggett's book.
Ah, okay, yeah. I didn't look at the book, but yeah. But I mean, the argument is pretty simple. Okay, so starting from here, we can construct the Spinnaker. And the argument goes like this. Okay, imagine that I start from a PCS superconductor, but I like to have a specific system where the average number of electrons per site is 1. Okay, so remember that in superconductor, charge is not a good quantum number. So you cannot talk about definite charge, but you can definitely talk about the average charge. And here, numbers are fluctuating, but I can think about an average number. And I like to have a one, on average, I like to have 1 electron per site. So the lattice is half fill. Okay, so this is the real space wave function like this. And then what I'm going to do is I like to increase the electron-electron interaction to be basically infinity, so that I end up with exactly 1 particle per site. So if the electron-electron interaction is infinity, then I cannot have more than 1 electron per site. So when I do that, essentially what I'm doing is I'm freezing out all charge fluctuation. So I have some kind of projection here. I have now exactly 1 particle per site. So there's no charge fluctuation. Now charge becomes a good quantum number. So obviously such a wave function is, describes an insulator, right? Because there's no charge fluctuation. And then you can immediately see that such a wave function is essentially given by linear superposition of valence band covering. The amplitude essentially given by product over all pairing wave function for that given valence band covering configuration. Okay, so one way to think about this ground state wave function is also like this. Imagine that I put this, say, wave function on a cylinder. So initially, I had a superconductor on the cylinder like this. So I'm thinking about a 2-dimensional superconductor wrapped around the cylinder.
I have a question.
Yeah.
So in the previous slide, so when you write down the BCS wave function,
Yeah.
it has some sign structure to it, right?
Right.
So does it have a meaning in terms of spins? Does it mean like spin singlet or?
Yeah, so for example, this wave function has to be, this is a 2-particle wave function. So depending on the boundary condition, you have a different sign structure. For example, you can have, depending on whether you have a periodic boundary.
So if you just take the modulus of that.
Oh, this has to be, I mean, this wave function has to be anti-symmetric. Totally anti-symmetric. You can form Ionic wave function. But this is sort of already built into the wave function.
Yeah, but if you just take the modulus, do you still get some RV?
I think this is not a model. I think this is just not a modulus. It's just it can be a complex wave function.
Okay. Now I'm asking, if you take it, do you still get some sort of RVB?
You mean you want to take an absolute value here? I think that this amplitude already has a sign structure built into it.
Yeah, that's
and I need that because I need to make sure that the wave function is totally anti-symmetric, because this is a Fermionic wave function. And this is actually the RBB wave function. So I don't know what you mean by taking an absolute.
Because I mean the degrees of freedom you're considering just spin, right? They have bosons.
Right.
And if you don't consider this any sign structure there, do you still get a superposition of? You get still a superposition of so many spins.
I think you need a sign. I think you need a sign structure. You need a complex number. Yeah. If you take an absolute value, you basically screw up the sign structure of the wave function, and that's quite important ingredient in this wave function. The sign structure is extremely important. That really reflects the quantum nature of the wave function. Yeah, maybe we can, discuss that afterwards. So imagine that I put my superconductor on the surface of the cylinder, and think about another configuration where I thread HC divided by 2 vortex in the center of the cylinder. So in that case, your quasi-particle will see a pi phase shift, for example, in this case, and that's not the case here. So now take 2 systems like this. If you take a superconductor before projection, before you take the electron-electron interaction to be infinity, then typically such a state has a higher energy than this one. This one is usually ground state. This one is excited state. But when you do a projection, namely that you put electron-electron interaction to be infinity, then under certain conditions, these 2 wave functions may give you exactly the same energy. On the other hand, if you take the wave function overlap, the wave function overlap go to 0 in the thermodynamic limit. So if that happens, it's clear that I'm basically generating 2 degenerate ground state because energy is exactly the same in the thermodynamic limit, and the wave function overlap goes to 0. So there are 2 distinct wave function, but they give you the exact same energy. So in that sense, on the cylinder, you can generate 2 degenerate ground state. So that's the argument. So notice that in these 2 wave functions, no local measurement can distinguish these 2 phases. Basically, locally, there's really no distinction between these 2 states.
So what's the difference between these 2 wave functions in terms of this like the pairing function, the FRR and alpha?
Yeah. So it looks like this. So for example, I talked about the amplitude for each valence band covering, and for example, in this case, the wave function by construction has to be this parallel function has to be periodic in both directions, x and y. This is x and y. But for this wave function, in one direction, actually this wave function is anti-periodic. So they are, they are not exactly the same wave function. But nonetheless, they give you the degenerate ground state. Another way to think about this problem is to go to a short coherence length limit. So remember that I started from a superconductor. So I have an option of thinking about a superconducting state with the Cooper pair and having a very short coherence length. Imagine that the coherence length is as short as the lattice spacing. So in that case, if you take a linear combination, say symmetric and the antisymmetric combination of this wave function that I talked about, then one can show that they represent different kinds of sort of topologically distinct valence band covering in the following sense. For example, if I take the even combination like this, and imagine that I'm focusing on the single column on a cylinder, and I count the number of valence bonds that cuts this line. And for example, in this case, I have an even number of valence bonds cutting the line. Here I have odd number of valence bond or diamonds cutting the line. And by moving around these diamonds like this, and notice that, for example, here, I'm changing the number of diamonds cutting this line from 2 to 0. Sorry. 2 to 0. I have to do this, yeah. OK. So 2 to 0. But here, I'm changing from 3 to 1, for example, right? But the point is that you cannot go from this sector to the other sector. That's just impossible. So this is another argument saying that this type of ground state and that type of ground state, they are basically disconnected, topologically disconnected. And in that sense, this non-trivial ground state degeneracy essentially has a topological origin. So it's just that the two types of ground state just topologically distinct. So is it clear? Yeah. So you already know, but I'm just reminding you that that's essentially what happens. And what about elementary excitations? So remember that I started with superconductor with average number of electron per site to be 1. Now, if you in the superconductor, obviously the quasi-particles are Bohr quasi-particle. Since I have a sort of particle symmetry and the fact that I have exactly one electron per site, tells you that this Bohr quasi-particle has a 0 average charge. It's an equal superposition of particle state and whole state. But they carry spin-Hawk quantum number. So average charge we can talk about average charge for Bohr quasi-particle, even though the charge is not a good quantum number in superconductor. Now, I increase the electron-electron interaction to be infinity. Then notice that essentially the resulting quasi-particle will have exactly 0 charge because I'm coming from here. Then I'm freezing out a charge fluctuation. So I naturally get a particle that has a 0 charge, but it still carries a spin-Hawk quantum number. So this is one way to think about a quasi-particle excitation, the Spinnaker, and that has 0 charge, but the spin-Hawk quantum number is still there. So this represents the fractionalization of electrons, if you like. So that's one way to think about it. OK. So and you also heard about the symmetry protected topological phases. Again, I'm focusing on a gap phase here. So in this case, the argument is that if you don't, so argument is that these topological phases and simple phases, they may have the same symmetry. And if you insist that when I construct this path or unitary transformation connecting these two phases, if you require that along the path you should maintain the symmetry, the same symmetry, then there's no way that you can connect these two phases. But if you're willing to break it, say if you're willing to break this symmetry along the way, then you can in principle connect these two phases. So in that sense, whether this phase can be connected to the other depending on whether you require the symmetry or not along this unitary transformation. So the famous example is topological band insulator is protected by Ttire symmetry. So what that means is that this will be topological band insulator. This will be a boring band insulator. And they are protected by Ttire symmetry, meaning that if I require that the Ttire symmetry is maintained along the way, then I cannot connect these two phases. But if I'm willing to break that Ttire symmetry, I can, in principle, connect these two phases. So there's this simple example that demonstrates this. So this is the Dirac-Fourier Hamiltonian in 3 dimensions. These gamma matrices are 4x4 matrices. So the mass can be positive and negative. When you go from positive mass to negative mass, we have a transition from band insulator, trivial band insulator to a topological band insulator. So the Dirac-Fourier described that transition. Now imagine that I add another term. Here I have a gamma 5. Gamma 5 is a product of all of these 4x4 matrices. And you can show that this guy breaks Ttire symmetry. So if I use this parameterization, notice that if this parameter t is 0, then I have original Hamiltonian with a positive mass term. Say I start with the positive mass. At t equals 0, I have a trivial band insulator. If t is pi, then this guy changes sign, so I get a topological band insulator. But I can connect these two phases by adding this term. But the price I have to pay is that this term breaks Ttire symmetry, right? So this is an explicit construction that tells you that in principle I can connect trivial band insulator to topological band insulator, but I have to break Ttire symmetry to do that, right? Okay. So then I'm gonna switch the gear and talk about a connection to a real system. So we think that quantum materials with the strong SpinOrbit coupling may be the place where we can see the combined effect of electron interaction and this topological property to ground the wave function. So this is sort of the general setup, if you like. So I have some kind of a kinetic energy scale or band structure, if you like. And this electron-electron interaction here is represented by the famous Hubbard interaction. But I like to add one more ingredient. That's the SpinOrbit coupling. Okay. So we know what happens when you have an only interaction. Then you can have a transition from simple metal or band insulator to a mud insulator. This is the correlated insulator. Now we also know what happens when you only have a SpinOrbit coupling, a weak interaction. Then you can have a transition from, say, boring insulator to a topological band insulator, for example. So definitely there's a transition as a function of SpinOrbit coupling. There may be a transition as a function of interaction scale. So you can see at least there are two phase boundaries like this. Then the question is, what happens when you have both electron-electron interaction and strong SpinOrbit coupling? And this is the place where a lot of interesting things can happen. So this is what we call spin-orbit assisted mud insulators, and you can expect to see all kinds of exotic phases. The point is, in what kind of materials any of these phases can be seen, and these are 4D or 5D transition metal oxide system. So why this is interesting? So if you look at the periodic table, and this is the 3D elements, 4D elements, 5D elements. So we all know that if you go down in periodic table, the effective Coulomb interaction scale will decrease. The reason is very simple. When you go from 3D, 4D to 5D, the spatial extent of the d overlap becomes bigger and bigger. The system becomes more and more itinerant. The wave function overlap between d orbital becomes bigger and bigger, and that there's a better screening, so the effective U decreases. On the other hand, when I go down in periodic table like this, then atomic number increases, and we know that the SpinOrbit coupling goes like atomic number to the 4th power. So the SpinOrbit coupling strength becomes bigger and bigger. So when people looked at this 4D or 5D transition metal oxide system in 1960s and 70s, a lot of people thought that these are very, very boring material because basically your interaction scale comes down and the bandwidth is so big that these are probably weakly correlated electron system. That was the prejudice. But they didn't realize that you also increase the SpinOrbit coupling, and that essentially makes this material much more interesting. So for example, when you go down to 5D elements, your Hubbard U becomes small, like a 0.5 electron volt. But your SpinOrbit coupling is also about 0.5 electron volt. So there's a very interesting interplay between electron-electron interaction and strong SpinOrbit coupling. So another way to think about this problem, so here I'll be focusing on the iridium transition metal oxide, for example. So put this now, okay.
So are you always going to only consider atomic SpinOrbit coupling?
Yeah, here I'll be focusing on atomic SpinOrbit coupling. This one, this clicker is now okay. Yeah, so another way to think about this problem is as follows. So traditionally, we usually think of a 3D transition metal oxide or 4F lanthanide as a playground. And for example, iron nictide, high-tech copper oxide materials, the cobaltate and nickelate, they all belong to this category. Or the heavy fermion system belongs to this category. And in both cases, one nice thing about this system is that there's a separation of energy scale, like Coulomb interaction scale, crystal field splitting, and SpinOrbit coupling. They're all there, but they are typically different in terms of energy scale. And when we have a separation of energy scale like that, then then we have some good starting point to think about. But on the other hand, it turns out that if you go to 5D elements, then all these energy scales basically become degenerate. So I mean, this makes the problem more interesting, but at the same time, theoretical analysis becomes more difficult.
But it's already difficult with our view.
Yeah, that's true. Right.
So why do we push ourselves?
Because when all these energy scales compete each other, we expect to see more and more sort of emergent phases, right? And this is the place where you may actually see a more exotic phase of the matter that you guys all love and like to see.
So what is the energy scale for the fermion energy in the 5D?
So 5D material, the energy scale is the bandwidth is say. So I talk about this. So the effective bandwidth is basically slightly smaller than 0.5 electron volt. So actually even bandwidths can be comparable.
So I can just think about this using like the naive or simple equation to obtain some scale models.
Yeah. So what actually happens is that I'll talk about that, but essentially many materials like this pre-close to metal insulator transition. Basically, your Hubbard U and bandwidth can be comparable. Yeah, not always, but it can happen. Yeah. So let's start from some atomic physics. So I'm talking about here. I'm focusing on the iridium 4+ ion. So these are the 5D orbital. The outer shell is a 5D orbital. So in free space, of course, all of these 5D orbitals are degenerate like this. But in a cubic crystal field, they split into two pieces. So this is what we call a T2G manifold. This is called EG manifold. And it's pretty clear why those guys have high energy, because all these orbitals are pointing to the oxygen atoms here. There's a larger Coulomb interaction cost. Here they are always avoiding it, so that's why they are in a lower energy manifold. So the point is that if I think about an angular momentum operator in the 5D orbital, of course the angular momentum operator for d orbital is equal to 2. But if I restrict this to this D2G manifold, then some simplification happens. So this is the explicit form of L equal to angular momentum operator written in this orbital basis. And notice that if I project this to this T2G manifold, namely dyg, dzx, doxy orbital space, so take only this element, that's what we mean by projection. Then notice that it's essentially the same as L equal 1 angular momentum operator, except that there's an additional minus sign. Yeah, that's really the only difference. So if I restrict ourselves to here, then angular momentum of this d orbital actually acts like angular momentum 1 operator. So now I combine this angular momentum 1 with the spin half quantum number of the electron. Then I have total angular momentum either half or 3/2. And usually half J effect, the J half state has a lower energy. 3/2 state is higher energy in the usual angular momentum addition algebra. And if you think about the energy cost. But here they are opposite because there was an additional minus sign. So minus sign plays a very important role here. And then I have 5d electrons in the d orbital for iridium 4+ case. So 4 of them goes into the pseudo total angular momentum 3/2 state. The remaining one goes into this level. So this way I can generate basically half field pseudo spin half system. And that's very important, right? But this is just like a pure problem.
Can I understand where the minus sign comes from?
Yeah.
Some simple way.
I don't know whether there's a simple way, but so it just happens that the projection of this guy. So you can think about this as changing the G factor from 2 to -2. So in a way, I'm thinking about a very, very strong SpinOrbit coupling limit, but say, strictly speaking, I think that's the best way. Is thinking about this as changing the G factor sign from +2 to -2.
Why change it?
This essentially coming from the fact that the usual L equal 1 angular momentum, the wave function is a P wave like. This is a D wave. So if you look at the angle, if you think about the spherical harmonics, then there's a -1 sign change. Yeah, the spherical harmonics, has like -1 to the L something, right? There's some sign structure in it, so that's essentially the origin. Yeah. Right. Okay. Right. So the point is that you end up with this half field pseudo spin half degree of freedom, and they represent Kramer's doublet, just like ordinary spin, in the sense that they are time reversal partners, right? So that's why it's called Kramer's doublet. But in essence, it's some subtle linear superposition of all T2G orbital degree of freedom. And this orbital content is extremely important if I think about the interaction between this local moment. Okay. So in the band picture, so this is the atomic picture, if I connect all these iridium 4+ ions on the lattice, then you will get a band. So this is like a J effective 3/2 band that will be fully filled. Then I end up with half filled J effective half band. So if you believe this picture, then this material without any interaction should be metallic, half filled metal. But if you put some moderate strength of Hubbard U, you can open up a mud gap. Basically, this is the upper Hubbard band, the lower Hubbard band. And since the system is half filled, I end up with a mud insulator. So what is novel here is that notice that in the total bandwidth can be quite big because this is a 5D orbital. The d orbitals are very extended. So total bandwidth is quite big. But if you think about the effective bandwidth of this bandwidth can be so much smaller than that bandwidth. So we don't need a large Hubbard U to open up a gap. I just need Hubbard U that's bigger than this bandwidth to open up the mud gap. So even with the moderate strength of Hubbard U, I can still get a mud insulator.
But wouldn't that also bring in the lower, wouldn't you be mixing with the lower band if you bring in other other interactions.
So in reality, there's always some mixing between the half and 3/2 bands. So also, I will talk. I'll mention this. Here we have a very simple picture that I'm only putting a Hubbard U, but there's also a multi-orbital interaction that you cannot turn it off, and that multi-orbital interaction plays an important role when I'm thinking about connecting half and 3/2 degree of freedom. In fact, you will see later that the presence of this field band is extremely important when we talk about spin-spin interactions. This is a very simple picture. But the point is that you can have a Mott insulator with a moderate strength of value. Okay. Good. So here are some general ideas about this type of material. So the claim was that the moderate strength of U can also give you a Mott insulator. So that's important. And in fact, you can appreciate that having this strong spin-orbit coupling is a clever way to limit the orbital degeneracy. So for example, remember that here, if I have 5 electrons in the T2G orbital, if there was no spin-orbit coupling, then these orbitals are all degenerate. I end up with 5 electrons in these 6 orbitals like this. This is a very, very degenerate situation. And it's very hard to solve a problem like this, actually. But nature doesn't like orbital degeneracy. So what nature usually does is to distort the lattice in such a way that they get rid of all the degeneracy. But when that happens, the physics becomes really boring, right? So nothing interesting really happens in real life, even though you can construct a lot of theoretical model taking into account all the spin orbital fluctuation. That's typically called Coherence-Length model. And typically, what happens in practice is that all the boring phases shows up because lattice essentially distort. But here, using spin-orbit coupling, I'm basically naturally lifting the orbital degeneracy. Yeah. So it's a clever way of lifting the orbital degeneracy so that I end up with interesting quantum mechanical degree of freedom. So for example, this is a way that you could generate a spin-half moment, so pseudo spin-half moment. And that's the situation where you expect to see large quantum fluctuation. And that's one of the reasons why we think that this is a good place to look at quantum spin liquid state. Also,
in reality, does the lattice deformation not happen?
The lattice deformation does happen. So in fact, there is some mixing between spin-half and 3/2 degree of freedom can actually happen. Yeah. So we have to worry about that too. Okay. So now, if you just looking at the similarity to the Q-plane, if you dope the half-field J-effective half band, you can expect that you may actually see a high tissue superconductivity. This is one of the proposals by a center. Also, as I emphasized, these are weak Mott insulators in the sense that the charge gap may not be so big. So often, these materials are very close to metal insulator transition. And I think that's a good thing because basically by applying a pressure, for example, these materials are very, very sensitive to strain or lattice. So by some clever lattice engineering or making a heterostructure, you can change the electronic properties very, very strongly. It's extremely sensitive to the lattice degree of coupling to the lattice. Again, this is mainly because the d orbital is so big and it is so extended that it couples to lattice in a very efficient way. Also, because we have a strong spin-orbit coupling, often we end up with the semi-metals, or it can also be a topological insulator. Okay, so now I'm going to switch the gear and talk about what we call Ttire material. So the idea comes from these two gentlemen, namely that let's think about this particular material. This is called alpha. A means alkali ion, so A can be either sodium or lithium. So here, iridium ions are sitting on a honeycomb lattice. And what is important here is the oxygen octahedra around the iridium, they share the edge, not the corner. And so it turns out that if you have a system like this, then you can derive a spin Hamiltonian where you end up with an Ising interaction along different bond, but Ising interaction in a different quantization axis. So along the blue bond, the Ising interaction along the x direction, here's an Ising interaction along the y direction, Ising interaction along the g direction. And if you have an interaction like this, and if you solve a classical model like that, then you end up with exponentially large number of equally unhappy classical ground state. Essentially, this is a basically frustrating interaction. Yeah. And this model can be solved exactly. It's solved by Ttire. It has to be Ttire, right? Ttire. If anybody can solve this model, it has to be Ttire. But the idea is as follows. Why you have this interaction? So remember that my oxygen octahedral is sharing an edge. So this is iridium atom, and there are oxygen and oxygen. They have approximately 90-degree angle. If you have exactly 90-degree angle, then typically such a super exchange path will give you ferromagnetic exchange interaction. If it's 180 degree, it gives you anti-ferromagnetic exchange interaction. In this case, two exchange paths through this oxygen, that oxygen is symmetrically placed. And you can show that the leading super exchange interaction through this path and that path exactly cancel. So that the leading ferromagnetic exchange interaction is equal to 0. Christian?
So this is irradiates, and
Yeah.
you just told us a while ago that the Hubbard U is approximately 0.5 compared to the bandwidth.
Right.
So I would think that the hopping terms plays a role.
Right. So
because
it turns out that this particular material is much more insulating. So in this case, in this particular material, the Hubbard U is definitely much bigger than the bandwidth. Yeah. I mean, the actual bandwidth depends on the lattice structure, obviously, right? So in some material, bandwidth can be comparable to the Hubbard U, but in this class of materials, it's much smaller. So these are actually good insulators. Yeah. I mean, it's not a strong Mott insulator, but it's a reasonably strong Mott insulator. It's not a material that's close to metal insulator transition. Yeah. Okay. So then we have to worry about the next reading order. It turns out that you have to include Hund's coupling or multi-orbital interaction to derive this. In fact, what actually happens is that you have to include the J effective 3-hop manifold in the perturbation theory. Essentially, when you go from here to here and come back, you have to worry about the fact that you can also go to a J equal 3-hop state and come back. So that's the way the multi-orbital interaction comes into play. So by taking into account that hopping to the J effective 3-hop manifold and come back, you can derive this interaction. In fact, this K is proportional to the Hund's coupling. So if there is no multi-orbital interaction, you cannot get this interaction. Okay. So, but this is a model written in this way, and this model can be solved exactly. And so that's why this is called Ttire model. And the solution is very simple, so I can easily describe to you. So this model was solved by writing down the spin operator in terms of Majorana fermion. So there are 4 Majorana fermion you can use. So notice that if I use this representation, then this Hamiltonian becomes essentially 4 fermion interaction. So B, basically B, B, and CC. But it turns out that this combination commutes with the Hamiltonian. Essentially, it becomes a C number. Once it becomes a C number, then this is a quadratic Hamiltonian, and we know how to solve that. We know, the only thing we can solve in physics is free particles and harmonic oscillators. We already reduced every problem to 2 problems, right? So this is one of those things. So this is it becomes a free particle problem. The only thing we have to decide is what kind of constant of motion I have to use. It turns out that setting all the Uij to be +1 gives you the ground state. And another way to say the same thing is that you can think about a loop product along the, say, hexagonal loop or product of these operators, and they're also commute. And as long as this guy becomes +1 or -1, then you can reduce this problem to a free fermion problem. And the ground state sector is given by WP equals to +1. Okay, so ground state is in the 0 flux sector, if you like. If you get that, then the C Majorana fermion has this Dirac dispersion in it, just like a graphene. The Dirac point is at the K point in the Brillouin zone. Okay. So before I go on, I'd like to give you some ideas as to how to think about, more generally, how to think about a Spinnaker, especially how to write a variation wave function for this. So every important problem should have a wave function, right? Because BCS, there is a wave function, quantum Morse state a wave function. Every important problem is solved by writing down the wave function. Do you agree? So we need a wave function for this.
So can the ground state of the type model to understand the picture of this RBB diagonal covering?
This is what I'm going to do now. That's precisely what I'm going to do. Okay. So So how to write down a variation wave function? So it turns out that in order to do so, it's useful to use so-called Parton construction. So this is construction using, say, it's a fermionic Parton. This is not the only way, but this is one way. So you write your spin operator in terms of fermion operator like that. And if you impose the constraint, the number of fermion per side is exactly 1. Then you can faithfully represent the spin commutation relation. So at this level, there's no approximation. Now, you have a Hamiltonian, like Heisenberg model like this. You end up with 4 fermion interaction. And notice that this is like ultimate strong interaction problem because there's no kinetic energy term. You only have an interaction energy. There's no kinetic energy. So how to solve this problem? We have to make an approximation. So imagine that I do some sort of mean field theory. Then you can easily think about 2 types of correlation. One of them is in the particle Hall channel. The other one is in the pairing channel. So in a way, your fermion kinetic term is dynamically generated from fermion-fermion interaction. So if you do this kind of mean field theory, then the resulting theory is just usual BCS theory. Because I have a correlation in the particle Hall channel. I have a correlation in the particle-particle channel. The important thing is that I should satisfy the constraint. The real problem, the constraint should be satisfied strictly. But in the mean field theory, is satisfied only on average. Okay. So notice that this is essentially the same construction that I talked about. This is like a superconductor wave function. But I have to impose the condition. The number of particles per side is exactly 1. Right? So this makes the connection to the Mickey Mouse discussion about the quantum Spinnaker. Essentially the same thing. So this is one way to think about that. So in the mean field theory, you have some hopping amplitude and pairing amplitude. Those are dynamically generated. But it's known that not every choice of chi and delta are independent. You can actually make a gauge transformation between those parameters. So the mean field Hamiltonian has to be invariant under certain gauge and lattice transformation. So not every choice is independent. So it requires some classification. This is called PSG, projective symmetrical analysis. It's proposed by Xiaogang Wen. So Xiaogang would say, if the system is gapped, then this kind of system has a topological order. If the system is gapless, then he calls it quantum order. And I don't know what quantum order really means.
Can we go back to the Ttire model?
Sure.
Am I the only one who feels that it's going a little too fast? Is it?
You can ask questions all the
Yeah,
time.
yeah.
I mean, you are in the driver's seat. So.
This is, so that's the dispersion?
Yeah,
It's gapless?
it's gapless. So these represent the C fermion dispersion. And you can forget about this in the exact solution. What this represents is the fact that if I look at the P fermion dispersion, it's going to be flat because it's basically given by constant.
So the exact wave function, because it's exact result only,
Yeah.
the wave function, that's not going to look like RBB but right?
So in fact, you can recast this in this RBB form, and essentially that's what I'm getting into. So if you wait for like 1 or 2 minutes, then you will see the connection. Yeah, good. Yeah, okay. So the mean field wave function is of course not exact. So we usually say we have to project out the double occupancy. So if you do the projection, meaning I impose this constraint of single, exactly 1 particle per side exactly, then that projected wave function is the ground state wave function. And chi and delta can be taken as a variation parameter. And typically you want to find chi and delta that gives the lowest energy solution. So the mental picture, okay. So another thing I like to mention is that when we talk about spin liquid, we quite often talk about gauge theory. And the reason is pretty simple. If you go to a Hamiltonian like this with the pairing amplitude to be 0, imagine that you only have a hopping channel. Then you immediately notice that the Hamiltonian is invariant under U1 transformation, like this, the usual electromagnetic type U1 transformation. And because of that, you allow fluctuation of this phase of this chi parameter that represents the U1 gauge field fluctuation. So your spin-on, the fermions are interacting with U1 gauge field. On the other hand, if a pairing amplitude is non-zero, then you don't have this U1 gauge invariance. You only have a discrete gauge symmetry. Only, say, Aij, the phase of this chi, only 0 and pi are allowed. And this represents the eigengauge field. So the Hamiltonian is invariant only under this G2 gauge invariance. So that's why it's called this type of spin liquid is called G2 spin liquid. This type of spin liquid is called a U1 spin liquid. So going back to Ttire spin liquid, okay, one more thing. So when we have to think about U1 spin liquid, the projection of, say, free fermion, no pairing amplitude, G2 spin liquid will be a projection of the BCS wave function. So you can think about this as some kind of the map.
Sorry, why should I think that, so you have a symmetry, why is that symmetry gauged?
Huh?
You have a symmetry, the Hamiltonian,
Yeah.
why is that symmetry gauged?
Why symmetry is gauged?
Yeah.
Because you mean why there is a local gauge invariance?
Why? Yeah.
Because of the constraint. Remember that? So I didn't write down exactly.
Right.
Because you remember that there is a particle number. Exactly. Yeah. So when there is a constraint, then you have a gauge invariance, local gauge invariance. Yeah. Okay. So now I'm going back to a Ttire spin liquid. So remember that Ttire spin liquid was solved by writing down a Majorana fermion representation, not the complex fermion representation. So, but it turns out you can make a linear combination of those 4 Majorana fermions and making a complex fermion like this. And then you can see that, I didn't mention, but there was a constraint on the Majorana fermion. So the constraint was that if you multiply all 4 Majorana fermion, then there has to be -1. That was the constraint on the Majorana fermion representation. That constraint translates to that constraint. That constraint becomes this constraint. The number of fermions per side is exactly 1. So everything becomes equivalent. You can write down Majorana fermion representation spin operator like this, and you can rewrite it this way with this constraint. If you do that, then you can transform your Ttire model into this form. So there's the hopping part, pairing part, and there's exactly 1 particle per side constraint. Okay. So notice that this guy has a BCS form, and if that guy was 0, then I'm going to have a U1 spin liquid. But in Ttire spin liquid, delta is actually non-zero. And it's invariant under only this discrete G2 gauge transformation. So in fact, Ttire spin liquid, because of this, Ttire spin liquid is a G2 spin liquid. And this pairing amplitude, it turns out, is in the spin triplet channel. Not in the spin singlet channel. And this pairing amplitude is actually different for different bonds, 3 different bonds, because spin quantization actually changes. So detailed form you can easily read off from Ttire model. But what I'm trying to say is that you can understand the solution of Ttire spin liquid using this complex fermion representation, and this makes the connection to the usual picture of the Radioleng valence bond state.
But that dispersion was gapless.
Hmm?
The dispersion
That's right.
was gapless.
So this is an example of, say, gapless spin liquid, quantum order, according to Xiaogang.
So that's gapless and Z2?
Yeah. So this gauge structure has nothing to do with whether the system is the quasi-particle agitation is gapped or gapless. This just represents the gauge structure. So this gauge structure is always there. It's just that the quasi-particle spectrum can be gapped or gapless. It has something to do with the quasi-particle spectrum. You have to rediagonalize this to get a quasi-particle spectrum. But once you do that, essentially what you get is a C fermion. So once you diagonalize it, then you go back to the C fermion representation that gives you Dirac fermion. So one way to think about is that if this superconducting Hamiltonian, so to speak, has a quasi-particle spectrum that has a Dirac fermion dispersion in it, just like a D-wave superconductor. It's just that this one is not spin single superconductor. This one is like a spin triple superconductor. Yeah. So as far as the quasi-particle spectrum is concerned, there's no difference between this type of Hamiltonian and BCS Hamiltonian. It's just that once you solve this model, then the quasi-particle spectrum has a Dirac fermion spectrum at the K point in the Brillouin zone.
So your F fermions are not the spinons, right?
Huh?
Your F fermions are not the spinons here.
Okay, so these F fermions are spin-on, but you have to be careful here because if you're solving a Heisenberg model or any model that has a model that conserves the G component of spin, the spin is a good quantum number. So if you have a quasi-particle like a spin-on, they carry definite spin quantum number, right? Okay, but now the Ttire model doesn't have that. Ttire model breaks all the spin rotation symmetry. There's no U1 symmetry left. So the quasi-particles actually don't carry a definite spin quantum number. Strictly speaking, I think we shouldn't call that spin-on because they don't even have a well-defined spin quantum number. They carry entropy. They carry definite entropy. It contributes to the thermal conductivity and heat capacity. But it's not a spin-on in a traditional sense. But morally, they are the same.
But your mean field theory is exact, right?
Yeah, so here my mean field theory is exact because delta in T is basically fixed in the Ttire model. The usual case, this amplitude are fluctuating. The Ttire model, they are essentially fixed.
Is it because Ttire model is secretly a free model?
Yeah, so what happens is that in the Ttire model, essentially you don't have gauge fluctuation. So the Ttire model is the model where mean field theory becomes exact, if you like, so by construction. Yeah.
You have local gauge invariance, right?
Yeah.
You want, and it is only when we have this constraint with sum of average equals 1. So only this constraint imposes the local symmetry. Otherwise, we could have a global one, right?
That's correct. That's correct. Okay. Yeah. Good. So okay. So now yeah. Question.
So for the previous one, after you constructed from the B and the C fermions,
yeah.
This is exact.
This is an exact mapping.
And you can also construct this mean field theory by just using the normal
right.
spinner.
You could have done that.
Oh, so you cannot do that for. So is there any connection between these two methods for the
basically, they agree. So, for example, you could have solved the Ttire model just by starting from this representation. That's the question. Yeah. So I could have solved this model using this representation, and in the end, basically they match. They has to because they're related by this exact mapping. Yeah.
So,
question.
Yeah, but for this one, it's
yeah.
constructed by the B and the C Mariana.
Yes, sir. But in the end, if you rewrite your Ttire model using this representation, then you end up with some four-formula interaction. You decouple that in a particle-hole and particle-particle channel. It looks exactly like that. Okay. So now what you have to show is that the structure of this T and delta are exactly the same as the Ttire model and this one. And there, what we call, the thing that I mentioned, projective symmetric group plays a very important role. So for example, on the honeycomb lattice, if you start from this representation, and try to classify how many G2 spin liquids are possible. I think the number was like 180 or something like that. Huge number. But only one of them is comparable with this Ttire solution. And you can see that that PSG essentially agree with the Ttire solution. So there's one more step, but it can be done. Yeah. I try to simplify the problem, but there are more sophisticated questions. Yeah.
So if I want to think of this topological order in terms of some deconfined phase of a gauge theory,
Right.
so is it okay to write it in terms of this little a field, little a gauge? So if I don't know, so I'm asking whether if you can integrate out fermions, then would you get a deconfined phase for this gauge theory in terms of A?
Yes. In general, the answer is yes. For example, if this was a U1 gauge theory.
So then here you said F is gapless. So you cannot really do that. So I mean, is it clear to see that you get a deconfined phase for the A field?
So in this case, we know that this model, in the case of Ttire model, we know that this is in the deconfined phase because you're basically freezing out the gauge fluctuation. Gauge field is basically static in the Ttire model. So there's no confinement in that case. But generally, yes, in principle, you can have confinement, deconfinement transition. And a priori, you don't know whether the resulting state is in the confined phase or deconfined phase. But in this case, we know the answer because the model is exactly solved, right? Yeah. But generally, that's a difficult question. For example, in 2+1 dimension, we know that if your theory is a U1 spin liquid, imagine that you have a U1 gauge fluctuation, but the spectrum is gapped, right? Then we know that such a theory is just unstable. Essentially, there's no spin liquid like that. It's just unstable because of the gauge field fluctuation. This is the famous Polyakov confinement problem. Polyakov showed that because of the gauge fluctuation, this is what we call an instantaneous effect. Basically, all the fermions are confined. So this fractionalized agitation just doesn't exist.
Yeah, in the absence of turn sign. Yeah.
That's right, but then you have to break symmetry.
Oh, okay.
Yeah. Good. Yep. Right. So the point is that in real life, it's not just that we have a Ttire Hamiltonian. There are all kinds of other terms in real materials, right? So it'll be nice if this is the only term in the Hamiltonian, but that's typically not the case. You can also have other terms. So important question is whether by adding this term, you're going to kill this Ttire spin liquid or not, right? If it's immediately killed, then this basically not very important practically. So for example, if you add the Heisenberg term on top of the Ttire term, you can show that close to, as long as this term is not too big, the Ttire spin liquid is basically stable. So there's a finite area in the phase diagram where spin liquid is robust, right? And you can easily understand why this is the case using some kind of renormalization group argument. Basically, in this Ttire solution, your quasi-particles has a Dirac spectrum in it, so the density of state is very small. So any short-range interaction is basically irrelevant in the renormalization group sense. You need a strong short-range interaction to overcome that. So that's the reason why there's always a finite area where your spin liquid can be stable. That's a good news, because what that means is that you can add all kinds of other terms, but as long as these terms are not too big, then most likely that you have a finite region in the phase diagram where Ttire spin liquid is stable. Okay. So that was the picture. So there was an experiment actually done by Radu-Kollea. He did neutron scattering on this material, sodium iridate. And the ground state is unfortunately is not a spin liquid, but he found the magnetic order state. So initial expectation was that, well, if I add the Heisenberg term, that's always present. Either you get a simple net ordering or what we call striping antiferromagnet. what is found in the experiment is none of those. Surprise, surprise. But that's typically what the nature gives us, right? So, so yeah, it's basically what I should say, humiliating all theorists, right? That nature is humiliating all theorists. Nature got something else, and that's because, in fact, in real materials, lots of things happen. Like there's a lattice distortion and the mixing and everything. So it turns out you have to consider a more general model, and this is what this is. It turns out that this is actually a sort of minimal model. So there's a famous Ttire interaction. There's a Heisenberg interaction. It turns out that it's extremely important to add this term. This is called symmetric anisotropic interaction, but name doesn't matter. For example, along the G bond, remember that Ttire interaction has to be SG Ising interaction. Along that bond, this interaction is like SIX SJY plus SIY SJX, that kind of term. So if you're familiar with the Zalotninsky-Moriya interaction, Zalotninsky-Moriya interaction is a minus sign here. This is a positive sign here. It turns out that minus sign is not allowed by symmetry, but positive sign is allowed by symmetry, at least for the nearest neighbor bond. So you can derive this model starting from this J effective half, J effective 3/2 basis. You just do a second order perturbation theory, just the way that you derive Heisenberg model from the Hubbard model. You start from a multi-orbital Hubbard model. Then you do a second order perturbation theory. Then you can derive this Hamiltonian. And these are, you don't need to know. I think you don't want to know. But basically, these are all symmetry allowed terms. So because of all that term, for example, if you add this term, you can explain why you get a zigzag order instead of simple narrow ordering or the stripy ordering. Yeah. Okay. So currently, there are a number of material candidates for this Ttire Spinnaker. So there's a 2D honeycomb lattice of iridium. Here is the sodium and iridium version. There's a new player here. If I have time, I will talk about this. It's called ruthenium chloride. So ruthenium is a 3+ ion. And even though this is a 4D element, there's a strong SpinOrbit coupling. So the local moment of ruthenium ion turns out to be described by the same J effective half degree of freedom. And this material, for this material, there's a neutral scattering experiment. They see some sort of scattering continuum. I think I may have time to explain this. Also, Hide Takagi in Max Planck Institute, they took this material, then to put hydrogen between these honeycomb layers and do some magic, then magnetic order disappeared. So this zigzag order is gone. So the hope is that the resulting ground state of this material may be a Spinnaker. So this is under active investigation. It could be a boring paramagnet, but all the experiments suggest that it may not be a boring paramagnet in the sense that when you do an NMR experiment, for example, NMR night shift seems to be constant. 1/T1, the NMR relaxation rate shows some interesting temperature dependence. So it looks like it's not a boring paramagnet. I think that some theorists already have a theory. What kind of spin linkage it is. So this is a candidate. And another thing I will talk about later is there's a 3-dimensional version of this. So this is 2D honeycomb system. There's a 3-dimensional version of the honeycomb lattice. One of them is called hyper honeycomb. The other is called stripy honeycomb. You can make lots of them, like super honeycomb, hyper honeycomb, ultra honeycomb, right? But this is one of those. So this is the different polymorphs of the same material, the same chemical formula, but the structure is different. So that's why I call alpha, beta, gamma. They're all different. And the point is that under high pressure, both material under high pressure, the magnetic order disappeared. And the resulting ground state may be a quantum Spinnaker. So that's one topic that's on the very active investigation for now. Actually, how much time do I have? I have a negative time?
I'm trying to.
Yeah.
Oh, yes, you have the.
Yeah. I think I have a negative time.
Yeah.
So maybe I should
You stop here.
maybe I should stop here. And then in the next lecture, I'd like to describe some details of this experiment and try to see whether there's a way to understand this experiment using the theoretical concept that we developed in this lecture. Right. Thank you very much.